All right, we're going to get started. Welcome back, all of you, all of half of the class that's here today, to the last day of the third week of class. So, it's pretty real at this point. 3 weeks, that's some severe time. That's almost a month. So, we're in school. Like, the semester is going, and things are going to happen soon. We have the rest of chapter 3 to finish today, and then of course chapter 4 next week, and then the first exam. So chapter 4 is, I might have mentioned last time, it's a little bit more abstract. The model itself is not necessarily completely intuitive. It's like very specific to an approach to modeling the decision to consume. So it's the model that helps us to like decompose the behavior of consumption. So it gets us behind the demand curve, and it provides a lot of insights, and it's a really powerful model. But you need to build it up, and we're going to cover it over 2 days or whatever. But again, like, because maybe a lot of you maybe haven't been exposed to it yet. I would suggest getting ahead this weekend, either reading ahead or getting ahead in the lectures, because you can. I have playlists, as I might have mentioned, on my YouTube channel from last year. Like, you can get ahead on lectures as well, and just kind of start getting familiar with that model if you haven't seen it before. I do cover it in my introductory micro course, but others may not, or maybe they'll just lightly gloss over it. It's not ridiculously difficult or anything. It's just there's other stuff we're covering. And so, next week should be about you kind of starting to gather your thoughts and preparing yourself for the first exam, which is going to be, the beginning of the following week. So, and then there's homework assignments as well. So I'm going to open up chapter 3 and chapter 4's homework today, definitely today when I get back to my office. So you'll have an opportunity to get ahead if you want to. Everything's about you having the opportunity to do what's right for yourself. Whether or not you choose to do that is up to you. You have to decide, I'm going to spend time this weekend already starting to prepare for an exam that's, a week away. It's a good approach. It's a good thing to do. You don't want to leave things to the last moment, especially not in like upper division courses like this one, that are highly technical and have their own sort of language and approach and tools that are very specific to this approach. And so I hope that you will make the right decisions for yourself. But I will open up the homeworks. Also, just a reminder, Piazza deadline to register is Sunday night. Make sure you do that. And then the first 3 assignments will be due the middle of next week, and then the 4th one will be due at the end of next week, the homework. And then I'll also open up a mini paper for this chapter. They'll be due, I think next Thursday. Next Thursday is when that will be due. And then the 4th mini paper I'll open up and have that available. I won't open it up today, but when I do, it'll be available post the first exam, so you have a little time to write it. And the exam doesn't get in the way of that. So I will make adjustments to, my schedule of when things are due or whatnot. But again, remember, mini papers, you choose 3, so you'll see due dates, but obviously you don't have to do all of them, just the ones that you choose to do. So, and then there's an open chapter submission option, which means you can go back at any time during the semester and choose a prior chapter to write a paper on to give you a little bit of flexibility there. Ultimately, it's about getting you to write a rough draft of your paper prior to the end of the semester, when there's 1,000 things due and you wind up not writing a great paper. Yeah.
Even after the 2 weeks, correct? If I decide later that I do want to do one of the mini chapters,
that's for the open chapter submission option. So you can submit any chapter anytime into that option. Yeah.
But only one chapter.
Only one. Yeah. Only one. All right, are there any questions about anything you'd like me to address before I move forward with the material for today? All right. So we started covering chapter 3, quantitative demand analysis. I established the nature of the various elasticities. I'll do a brief review of that right now. and then we'll jump into how we can get elasticities from demand functions, and then we'll press very pointedly into the approach to like extract these elasticities from actual data that you can use to estimate demand functions. So it kind of bridges the gap between the abstract theoretical stuff and the more practical stuff. But it does get technical with the regression stuff. That's a statistical approach. So you've all taken statistics, so you have some foundation for it. I expect you to do any kind of statistical analysis in this course. I'll just like mention that you can and how you can do these things, and then talk about the various diagnostic statistics that are generated when you do this kind of statistical analysis that provide you insights into how predictive your work is of like a broader sort of market beyond what your data is telling you. So yeah, I'll be very specific about it. All right, so previously, again, we started talking about the different elasticities, how sensitive one variable is to changes in another variable, but of course the ones that are most relevant to demand. So we looked at the own price elasticity of demand. How sensitive is quantity demanded to changes in price? We know that an elasticity is the relationship between a percent change in a variable relative to a percent change in another variable. In this case, the percent change in quantity demanded over percent change in price. And we established that you can derive an expression that is equivalent to this, that includes the slope of, in this case, the demand function. So the change in your quantity demanded with respect to the price times the price and quantity you're looking at. So you'll be looking at a particular point. You want to figure out, well, how elastic is demand at that point? You would plug these in and then plug in the slope for the demand function, and then you would get the elasticity. And we'll figure out how to get this information today from the regression stuff. But that was one measure of elasticity we covered. In general, the magnitude of an elasticity is described in very specific ways. If it's greater than 1 in absolute value, we say that demand is, well, if we're looking at the own price elasticity of demand, we say demand is elastic. If the elasticity is between 0 and 1 in absolute value, we say that demand is inelastic. And then if it's exactly equal to 1, we say that it's unit elastic. And remember, we're talking about a relationship between quantity demanded and price, which is an inverse relationship. As one goes up, the other goes down. So the own price elasticity of demand will always be negative. So it's about looking at absolute values, the distance of a number from 0 on the number line, to be able to characterize the result as either being elastic, inelastic, or unit elastic. Yeah.
The more specific an object is, that makes it inelastic, correct? Like if you just want toothpaste, or if you want like pressed mint flavored toothpaste.
Right. So we talked about that last time as well, where it's like the broader defined commodity is going to be more inelastic than like a specific sub-product of that. So yeah, like a specific type of toothpaste will be more elastic than toothpaste in general. Right. It's not possible in practice. Theoretically, it's possible. I'll cover that case when we look at the model next week, which talks about like the decision to consume, and under some really strange circumstances that could happen. But it's so rare that like even in the one case that does exist in nature, sort of. It's still contentious. People debate it. Like it's not clear. There isn't a consensus about it. So really, no. Ultimately, is the answer. But we have to be very specific about. Yeah, there's a possibility. It's 0.0001111. Probable, but whatever. It exists. Yes. Price and quantity. Price can go up and quantity demanded. Price can go up and quantity demanded can increase in a very theoretical case, but in reality, generally no. All right, we talked about the relationship between elasticity and revenue and how sort of powerful this basic insight can be via the total revenue test, which tells us that if prices are high, demand will be elastic. If prices are low, demand will be inelastic, and somewhere in between, demand will be unit elastic. Here is total revenue. Over the elastic range, if we're lowering the price, then total revenues will increase. But over the inelastic range, if we're lowering the price, total revenues will decrease. We also talked about the fact that demand can change along a demand curve, but the steepness of the curve itself also tells us something about the elasticity of the market for a particular good, how sensitive people are to changes in price in a particular market. So the flatter the demand curve, the more elastic demand, with the extreme case being the perfectly horizontal demand curve, which we say is perfectly elastic, and it's as sensitive as possible to changes in price. Price changes by a penny. Quantity demanded goes down to zero immediately. Or demand can be as inelastic as possible or perfectly inelastic if it's a vertical line. And those are situations where people do not respond at all to changes in price. They are willing to buy the good no matter what the price is. And it has everything to do with, how much they need the good. Generally, this will be the case of like life-saving goods. The three things that affect how elastic demand is the availability of substitutes. Can you find things that will substitute for your good when your price goes up? If you can't, demand will be more inelastic. If you can, if there's a lot, demand will be more elastic. Time, how long people have to find alternatives. In the short run, in the short term, whatever the time period is that you initially find out about a price change, it'll be more difficult to find an alternative versus in the long term, where you can seek out alternatives. And then finally, how big of a portion of your overall expenditure is the good you're looking to buy? Is it a large part, like your housing? If so, if the price goes up, you're going to be very sensitive to changes in price, versus salt, which is like a minuscule amount of your budget. Therefore, you're not going to be very sensitive to changes in price. So, Gesundheit. So those are the three factors that affect the elasticity. We also talked about the relationship between marginal revenue and elasticity. Marginal revenue being the extra revenue gained by selling additional units. If you have a downward sloping demand curve, you have a downward sloping marginal revenue curve. That's exactly halfway from the horizontal intercept of the demand curve. It's twice as steep. And what we established was that over the range of elastic demand, marginal revenue will be positive, which again corresponds to that total revenue test property that says that as price goes down, total revenue goes up. Marginal revenue is positive. Marginal revenue is the slope of total revenue. And so, of course, it's going to be positive as you're lowering price. Marginal revenue will be increasing. When marginal revenue is equal to zero, so it hits the horizontal axis, then that corresponds to the point where elasticity is equal to 1. And that also corresponds to the point where total revenues are at their maximum. Because whenever a curve is at its maximum, its derivative, like the slope of the curve, is going to be equal to 0. And so that happens at the point, again, that corresponds to the point on demand where demand is unitary elastic. And beyond that, when demand is inelastic, marginal revenue is negative, which again corresponds to that range over which total revenues are decreasing as price is being dropped. And then we talked about the mathematical relationship between them, which is embodied in this relationship here. We talked about the cross-price elasticity, how sensitive the changes in quantity demanded of one good to changes in prices of the other good. So X and Y, we know that if this is positive, then the goods are substitutes. If this is negative, the goods are complements. We talked about income elasticity, how sensitive changes in quantity demand are to changes in income. If this elasticity is positive, we know the good is normal. And if it's negative, we know the good is inferior. All right, let's jump into today's stuff. So in order to obtain these elasticities, we'll talk about the approach in a second, but let's say that we start off with just a linear demand curve. Remember, the alphas represent constants in the equation. So And we also know that our elasticity is equal to this expression here. That's equal to the slope times the price over the quantity. So in each of these terms, like this one here, this is basically telling us that as price changes by 1 unit, then quantity demanded of good X will change by alpha X. So alpha X is the coefficient, it's the slope parameter, it's the marginal effect. There's a lot of words for it. But again, that's ultimately what that information is telling us. So alpha X is essentially this what we're looking for here, the derivative of the demand function with respect to price, the slope of the demand function with respect to price. So remember, yeah. So here, this is the notation of just change, and then in calculus, these are equivalent. It's something that's established in a calculus course. So this is just another way of writing the slope of the or the derivative of the demand function with respect to price. So again, this term is going to equal that alpha X. And so the own price elasticity of demand can easily be gotten by taking the slope, the coefficient of the price variable, and multiplying it by the price and quantity at any particular point to get, the elasticity at that point. And remember, that information is important because a firm can then figure out, can I raise or lower prices in order to increase my revenue? So that total revenue test can be checked via this information that you can get from this statistical analysis we'll talk about in a second. And you can also get the other elasticities from a demand function. So here's the price of a related good. So the price of some good Y. And again, alpha Y tells us that as the price of Y goes up, quantity demanded of X will either go up or down depending on whether the goods are substitutes or complements. But this is essentially, so if we were to do this whole thing again, but just have the price of Y in the bottom, then you would get a similar expression. And so this term here, which would be the change in quantity demanded of X over the change in the price of good Y, which is equal to alpha Y, can simply be taken from the equation, and then you put in the price of Y that you're interested in, the quantity of X that you're interested in, and you get the elasticity. And then finally, income elasticity as well. Alpha M represents the slope of the demand function with respect to income. As income changes by 1 unit, how much does quantity demanded change? Well, the sign will tell us whether the good is a normal or inferior good. But alpha M is the slope of the demand function or the derivative of the demand function with respect to income. And so you can get that information from a demand function. So alpha M is this term, but dq dx over dm. And then multiplying that by the amount of income and the quantity demanded at that income will give us the income elasticity. So you can, again, extract income elasticities this way, but there's an easier way, which I'll talk about in a second. So this is a linear demand function. So for a linear demand curve, the elasticity of demand with respect to a given variable is simply the coefficient of the variable multiplied by the ratio of the variable to the quantity demanded. Along these curves, as we know, the value of an elasticity depends on a particular price and quantity, which is calculated as we learned earlier. So the elasticity will change as you're moving along a demand function, even these other elasticities, not simply the own price elasticity. And again, it has to do with the fact that even though this is constant, these will be changing, and so that will affect the elasticity as you're moving along the relationship. All right, so that's a linear demand function, and as I've stated a few times already, demand functions don't have to be linear. They don't have to be a line. They might be like quadratic. They might be cubic. They might look differently depending on the market that you're operating in. People will behave differently towards different goods, and so the relationship between these variables and how much they're willing to buy will look differently. So let's say, so managers frequently encounter situations where a product's demand is not a linear function of prices, income, and other demand shifters. Suppose the demand function is not a linear function, but again is given, but instead is given by this expression here. where quantity demanded of good x is equal to the product of all of these variables times some constant, and then each variable is raised to the power of its marginal impact. So instead of the coefficients affecting it multiplicatively, they're affecting it exponentially, and all the terms are being multiplied instead of added. So C in this case is a constant, as it always is. What we can do with an expression like this is we can take the natural logarithm of the equation, and then we can obtain an expression that is linear in the logarithms of the variables. So if we do that, we're going to get this expression here, and I'll show you how to do that in 1 second. So we'll get this, what's called a log linear expression. Beta naught is still the constant. So the constant, we've taken the natural log of the constant. We've taken the natural log of some number. And since our constant is always just some number, we can just say, well, then the log of some number is just some number also. And then we can get these other terms by taking the natural log of these terms as well. So this relation is called the log linear demand function. And it's very useful because it's easier to extract elasticities from it, which I'll show you how to do. Well, you know, people might react one-to-one to changes in price. Like their quantity demanded might change by the same proportion as you move along the range of prices that you could charge. Or over high prices, like they might not respond too much, but then they might respond a lot more to low prices. So you'll get like a curved demand function versus like a linear demand function, and that's just representative of what the market is doing. And we'll look at that in a bit, where we actually have data points, and then we can see how the data points imply a line versus imply like a curve relationship. So that's how you do it. You do it by analyzing your market, getting data, and then kind of seeing what that data looks like, and then ultimately trying to estimate it via some equation, either a line if that fits best, or a curved relationship that might fit better. So I'll show you about that. It just depends. It depends. Yeah, it depends. All right. So quick review of logarithms. So the logarithm of x to the base of b is the number y, satisfying this expression here. So essentially, what we're trying to figure out is what number do we raise b to get x, and that's what the logarithm is trying to solve for. So we write the logarithm function of x as y equals the log of x with base b. So again, we're trying to figure out what number do we raise the base to in order to get x, and that is y. So that's the logarithm of x base b. And it is the inverse function of an exponential function for those math people. So if you have any kind of exponential form, basically here we would have log of 25 base 5. So we're trying to figure out what do we raise 5 to get 25? Well, the answer is going to be 2. So that's how we would write the log of that. So 5 raised to the power of 2 gets us 25. So a special type of log has the base of e. E is like a mathematical constant, kind of like pi, that's like used often. There's a way to derive it. I'm not going to show you because it's complicated, but it has a lot of mathematical meaning. But if we're looking at a log of something with the base of e, then we refer to that log as a natural log. Or we can just call it the log function. And it's denoted as ln of x. So when you have a log of base e, we denote it ln of x, where e is this mathematical constant. Like pi, there's a reason for this number, and you can derive it if you want to, but I'm not going to do that here. I'm just kind of giving you some information about the mathematics that underlies like some of the stuff we're doing in this chapter. So anyway, so the natural log is, again, the log of some number with a base of e. But we just write it ln of x. So here are some relevant properties of logarithms. So if you're taking the log of some number, and that number can be deconstructed into the product of two other numbers. So you have some number, maybe 8, and you can deconstruct it into the log of 2 times 4, let's say. Then that is equivalent to this expression here, where you have the log of m, and we're leaving the same base here, so the log of m plus the log of n. So you can separate this expression out into this, into that sum of those two logs. If you have the log of some number, base b, whatever, the base never really matters. The log of some number raised to the power of r, let's say, some power, that is equivalent to this expression here. So you can take the power of the m term and then kind of bring it out outside of the log and essentially be multiplying the log by that power. And these are equivalent. So it's just based on properties of logarithms. So that's my quick review of logarithms. So let's go back to what we were talking about here. Again, suppose the demand function is not a linear function, but instead is given by this expression here. So we can take the natural log of it. So taking the natural log, we just basically, notationally, it looks like this. We take the log of the dependent variable and the log of the expression that represents the independent variables affecting the dependent variable. And here we have the log of a bunch of terms being multiplied. So we can separate those out as the sum of the log of each. So I did that. So here we have the log of c plus the log of px raised to the power of bx, etc. And now, of course, from that last property I just covered, you can take these powers out and bring them out in front of each of these terms, again, just based on the properties of logs. And therefore, you can derive this expression here. And again, ln of c, the log of some number is just some number, because again, we don't know what the number is. It's just some constant. And so we just replace the log of c with beta naught. And then we have all of the rest of our terms with, again, the marginal effect, the beta x on the outside, multiplying the log of each term. So this is equivalent to this via the property of logs by taking the log of each side, which is something you can do mathematically. So that, again, the relation is called a log linear demand function. And why it's important is because it makes it really easy to get our elasticity. So when the demand function for good x is log linear and given by this expression here, the elasticities are, so the own price elasticity of this relationship here is actually just beta x. So when you have the expression in logs, so we have a log linear demand function, then the coefficient on our log of, let's say, the price of x is going to be the own price elasticity of demand. So you don't need to get it and then multiply by the price divided by the quantity. No, it's just, you can do a statistical analysis, estimate what this term is, and then that term is your elasticity. So you can easily calculate an elasticity from like market data. Again, the other ones that we're interested in, the cross price elasticity is just beta y. It's just a coefficient on the log of the price of the related variable. And the income elasticity is the coefficient on the log of the income variable. So that's why it's useful to do this. That's why it's useful to understand how to do it. And again, the form of the actual demand will be different depending on the market one's operating in, and it could be different on any given day. On one day it might be linear, another day it might be log linear. It's just you have to analyze the markets to figure out. So you can't just say, well, it's like rule of thumb, you're going to see this kind of demand here and then this kind of demand there. That's what all this is about. It's about using statistical analysis to figure out what are you dealing with in any particular case. So notice that when demand is log linear, again, the elasticity with respect to a given variable is simply the coefficient of the corresponding logarithm. All right, now let's talk about how we can get this information and the sort of the properties of the approach that allow us to say this is valid, even though there are assumptions made that you know, are sometimes called into question by people that maybe are skeptical of the results that one gets via the approach. There is a consensus about the legitimacy of this approach. So overall, it does have a lot of power, a lot of applicability. Unless you're at the level where you're like trying to advance the methodology, concerns about its overall legitimacy are not really relevant. But they definitely always need to be mentioned. All right, so the preceding analysis assumes that the manager knows the demand for a firm's product. In fact, we've been assuming that all along. As a manager, you may obtain estimates of demand and elasticity from published studies. You may not even have to do a statistical analysis. If the market is clear enough as sort of like a generic market, then you can just take elasticities from published studies, or you can hire consultants to estimate demand functions for you. Another option is to enter the data into a spreadsheet program and click the regression toolbar to obtain an estimated demand function along with some regression diagnostics. So you can easily actually do it with Excel. The function to run a regression is not just like there, like you have to activate it in the properties, which is silly. But whatever, like if you are interested in doing a regression analysis on something, just do a quick Google search. How do I turn on the regression function on Excel? And then it tells you, oh, go to the properties, and this is one hidden thing that you have to kind of find, and then say, yeah, I want to see this, and then it'll show up on your toolbar as a regression option, and then I'll talk about how that works. But again, I won't expect you to do it, but you should know how to do it because it's useful. All right, so regardless of how the manager obtains the elasticities, it's useful to have a general understanding of how demand functions are estimated and what the various diagnostic statistics that accompany the reported output mean. So again, it's worth your time to understand this stuff, not necessarily because you're going to wind up doing it yourself, but because you might be around people that are doing it. There might be people working below you that are doing it. Your company might have hired somebody, and you might be given a report that has this information. You need to understand what it means and what's being done. Now, in order to understand it, it entails knowledge of a branch of economics called econometrics. Econometrics is sort of like the economics version of statistics. Like we kind of took statistics and like kind of pushed it forward for our own uses. Econometrics is a fairly complicated field. It involves a lot of like sophisticated math, but it's very much worth your time to learn. There are introductory econometrics courses here that I do recommend taking, and it'll go through everything we're covering here in a lot more detail with a lot more examples of the different approaches you can take with the method and different versions of it. So again, econometrics is the statistical analysis of economic phenomena. It's beyond the scope of the course to teach you how to estimate demand functions, but it's possible to convey the basic ideas econometricians use to obtain such information via an example. So let's briefly examine the basic ideas underlying the estimation of the demand for a product. Suppose there's some underlying data on the relationship between some dependent variable, Y, which is maybe quantity demanded, and some explanatory variable X. So let's say you have like some data, you've done some market analysis, you've looked at different parts of the market, and you've seen some different price quantity combinations. In this market over here, when the price was this much, people bought this much. Over here, when the price was this much, people bought this much. So you have a bunch of data points. So let's say you have 1, 2, 3, 4, 5, 6 data points, as you see here. So the points A through F do not lie on a straight line or even a smooth curve. So the points themselves are kind of scattered about, but if not looking at the line, if you were just looking at the data points, you can kind of see at the very least that there is a negative relationship between the two. As you increase one, the other one decreases. So that's definitely there. And you can kind of see that if you were to put a line through it, it does kind of estimate the relationship, but it's not precise. There is definitely some variation there. But it's close, it's pretty close. So the job of the econometrician is to find a smooth curve or a line that does a good job of approximating the point, so that then you can get that equation, so that you can use that equation to do everything we've been doing and more. So suppose the econometrician believes that on average there is, let's say, a linear relationship between Y and X, and there's some random variation in the relationship. So mathematically, this would imply that the true relationship between y and x is going to be a line. So you're going to have your standard uh, uh, expression for a line. So your slope, your constant. But then there's going to be this extra term here, e, which is going to represent the error, the amount that the actual data points vary from that line, which is going to be the distance from the line that's estimated here of each of these points. So the actual relationship that exists between these variables is this. And it exists throughout all, like, let's say you're doing a market analysis of and we're going to use the example of television. So let's say you're looking at how much people are buying televisions, maybe throughout the world. So throughout the world, in every single television market, this is the relationship between the quantity demanded of television and the price of televisions. It's fairly linear, but there is some error, let's say. So A and B are the constant and the slope that are not known. They are unknown parameters. It can be estimated. And E is some random variable, an error term, that we assume to have a mean of 0. So we assume that if you take enough data points, that eventually the distance between each point and this line that we estimate, if we sum them up and we say that this might be a positive distance and these are negative distances, that eventually all of those will sum to 0, and therefore the error term will ultimately not matter. All that will matter is that linear relationship. And that's an assumption that's made to justify the approach. So that's one of the areas where people sometimes try to attack the approach overall, but again, it's demonstrated very clearly over several decades that this is an approach worth using. It does provide insights that are valuable. But you always have to acknowledge that things aren't perfect. And if somebody is coming at you with information done through a regression and they say this is how it is, and they are not acknowledging, but there are some problems with the approach. There's some problems with maybe even the results I got because of the approach. Then that's problematic. So it's always good for a responsible analyst to just be forthright about the fact that this is my analysis, these are my results, but it was used with a method that can be considered imperfect. But you have to understand the stuff really technically to be able to attack it. So that's also important. You can't just say, well, it's crap. Anyway, the econometrician must find out the values of the parameters A and B. So that's the job of the econometrician, is to figure out what is this constant here and what is the slope? What is the relationship between the change in the one variable and its impact on the other variable? So then the econometrician uses a regression software package to find these terms, and the ones that they find minimize the sum of the square deviations between the actual points and the line. So there's some calculus involved in what the regression software is doing, and it's something that you would learn in econometrics if you wind up taking it. But essentially what it does is it tries to solve for the equation for a line that's going to minimize the distance of all the points. And once it does that, then it gets the constant and it gets the slope, which basically defines the line, the relationship that you're interested in. And what you get is called the regression line. The regression line is a line that minimizes the square deviations from the line and the actual data points. So the values of A and B that are estimated are generally denoted with a hat. We call it A hat and B hat. They are the parameter estimates. And the corresponding line that we've estimated is called the least squares regression. So the least squares regression line for the equation that we're interested in, that exists in reality, where there is some error, is going to be this relationship here. It's going to be the estimated regression line that's going to have some estimated constant, some estimated slope coefficient, and then no error, because we assume the error goes to 0. So the parameter estimates represent the values of A and B that result in the smallest sum of squares between a line and the actual data. All right, so to illustrate, suppose a television manufacturer has data on the price and quantity of TVs sold last month at 10 different outlets in Pittsburgh, let's say. So these are not in order, but like they've looked at 10 different stores, let's say in Pittsburgh, and they see that at a price of $475, people are willing to buy 180. At a price of $575, people are willing to buy 275 televisions. So you've got, in this case, there are 10 datums is what they call them. That data point is called a datum. All right, so suppose we regress quantity demanded on price. So what you would do in Excel is you would say, I want to regress column B on column C. It's really easy to do it. It's like very self-explanatory, but you know you can find tutorials online really easily. Figure it out. But you may already have covered. I mean, I know you covered it in your statistics class. It may have been covered in your gateway class as well if you've already taken that. Somebody said the systems management or something, systems operations management or something covers it as well. Okay. So you've touched upon these things in different times. Or not, it's fine. I just expect you to know very particular things here. All right, so let's say we regress quantity on price. So we're trying to figure out how price affects quantity. We'll get this kind of printout here. Down here are the coefficients, the intercept, and the price that have been estimated. Don't worry, I'll blow them up in a second. So the intercept of the demand function that A hat that we were looking for is estimated to be 1631.47, basically saying that the quantity demanded independent of price is going to be 1631.47. And that also tells us that there are some other variables that were left out, which we know. We know there's other things that affect quantity demanded besides just its own price. And so if we were to include more of them, that constant may go down. It depends. So the intercept of the estimated demand function is 1631.47. The estimated coefficient of price is negative 0.26. So that tells us that in this Pittsburgh market, as you increase the price by $1, people buy 2.6 less televisions. So the estimated linear demand function for TVs that minimize the sum of squared errors between the actual data points and the line through the points is then going to be this regress line here. So that's what we've estimated. So now we have a demand function. We have numbers. We can estimate consumer surplus. We can get elasticities. We can do all sorts of things. Plotting the points. This is the line that minimizes sum of squared errors. So again, you see with just the points there is a negative relationship, and this line does fit it pretty well. It's not perfect. There's some error there, some variation from the line, but overall it fits it pretty well. All right, so there are certain other statistics that are generated that help us to understand how predictive, how well this estimated line can explain not just our own data, but maybe this relationship overall if we were to do the same analysis on more data or do the same analysis on like similar data sets. So the table provides information about the precision with which the parameters of the demand function are estimated. So here's again our coefficients that are estimated, and here are the diagnostic statistics that kind of give us an idea about how predictive these results are. So the coefficients reported are, again, merely parameter estimates of the true unknown coefficients. So the true unknown coefficients are going to be those coefficients that are going to be in that actual relationship that exists in nature between all participants in these markets, in everywhere that you can analyze these markets. So that equation that we saw earlier with that E is the actual relationship. The constant and the coefficient are the true unknown coefficients. We don't know what those are. We just know what they are from our data. We don't know what they are in nature, in the world where, you know, you have, who knows, millions, billions of data points. Yeah. The constant? It's the y-intercept of the line. So the line would go all the way up and then it would intercept it there. Actually, I have it backwards here, so don't worry about it. Don't worry about what's actually being graphed there. Like, just understand the method and what it's doing. Don't worry about the actual graph. I have it backwards because I have quantity on the y-axis, which is usually the other way around. Anyway, don't worry about it. All right, so given different data generated from the same true demand relationship, different estimates of the true coefficients would be obtained. If you had 10 data points from television markets in New York, 10 data points from television markets in Texas, whatever, you're going to get a different estimated relationship between the variables. So the coefficients will be different. And again, they will not give you the true estimate of those coefficients. If you were to be able to do a statistical analysis of all people that were willing to buy televisions and all prices of televisions everywhere. All right, so let's look at this first diagnostic statistics first. The standard error of each estimated coefficient is a measure of how much each estimated coefficient would vary in regressions based on the same underlying true demand relation, but with different observations. So again, it tells us like how precise is our coefficient estimate that we got from our data. So the smaller the standard error of an estimated coefficient, the smaller the variation in the estimate given data from different samples of data. So again, if this is small, that means that if we were to run another regression with different data sets, then this would fall pretty close to what we got. Given a set of standard but somewhat technical assumptions about the regression model, which I won't go through here, and is something that you would learn in econometrics, and again, you have to make certain assumptions about how it's all working, how you've sampled your data, the assumption about the means of the errors that we assume to be 0, and some other assumptions that I won't talk about. Given that stuff, then the estimates are what we call the unbiased estimators of the true demand parameter. So given that we've taken this approach, the estimates that we have here are considered to be unbiased, meaning that the estimates are not specific to the data that we use. They are more general than that. They are unbiased to the analysis we are doing. All right, so standard error. Now we're going to look at confidence intervals, which relates to these two columns over here. So I like, as far as this stuff goes, like, you should just understand regression analysis in general, and then you should understand like what these statistical diagnostic figures are, like what they mean, like what standard error means, confidence interval, like what it means. All right, so given a parameter estimate, its standard error that we have, and the necessary technical assumptions, the firm manager can construct an upper and a lower bound on the true value of the estimated coefficient by constructing a 95% confidence interval. So again, these are estimates based on the data we have. We can establish a 95% confidence interval that'll give us an upper bound and a lower bound to what the data suggests would be the range over which the actual parameter in the true market that we're interested in would lie. So the coefficients reported are merely the parameter estimates of the true unknown coefficients, getting us to this principle. Rule of thumb for a 95% confidence interval. If the parameter estimates of a regression equation are, let's say, A hat and B hat, again, in this case, it's going to be the constant and the slope parameter, then the 95% confidence interval for the true values of A and B can be approximated by, for the constant, you add or subtract 2 times the standard error. So this is another Greek letter, sigma. Sigma is just a way to symbolically represent the standard error. So if we take our coefficient, 1631.47, and we add 2 times the standard error, we'll get our 95% confidence interval upper bound, so we'll get 2194.07. And if we subtract 2 times our standard error, then we'll get the lower bound of 1068.87. And so what that tells us is that we can then be 95% confident that the true parameter value is somewhere between 1068 and 2194 roughly. And so this is what we've estimated. This falls within that, but the actual true value in the actual big market that exists in the world lies somewhere between that. And then for the slope estimate, same thing, 2 times its standard error. So plus or minus 2 times its standard error will get us that confidence interval. So again, we've got an upper and a lower bound for that statistic as well, telling us that the actual impact of price on quantity demanded of television lies somewhere between these two bounds with 95% certainty. So again, these are the standard errors of A and B. So for instance, again, the table has these upper and lower bounds. I already talked about this. The parameter estimate for the coefficient is 2.6. It lies in the middle of those bounds. For this information, we know the best estimate of the price coefficient is negative 2.6. And so we're 95% confident the true value lies between negative 3.82 and negative 1.37. That's what the 95% confidence interval is telling us. All right. Then we've got the T statistic. So the T statistic is another sort of diagnostic statistic that tells us something about how predictive our estimates are, our coefficient estimates are. So the T statistic is the ratio of the value of the parameter, so the value that we've estimated, divided by the standard error of the parameter. So for example, the parameter estimates for A hat and B hat are the corresponding standard error, and the corresponding standard errors are sigma hat and sigma B hat. So these guys over here. The T statistic for A is going to be, for the constant, is going to be the coefficient estimate of the constant divided by the standard error. So that'll get us a 6.69 in this case. And then for price, it's going to be, again, negative 2.6 divided by 0.53, which gets us to negative 4.89 for the T statistic. So when the T statistic for a parameter estimate is large in absolute value, then you can be confident that the true parameter is not 0. So what it's basically telling us, the T statistic, is that if you were to run this regression several times on different data sets, that let's say we're talking about the price coefficient, that the actual impact of price on quantity demanded would never be 0, meaning that there is an impact of price on quantity demanded. That's what a large T statistic is telling us. So remember, this approach is not just for demand functions, it's for any relationship. So generally, like even though you might do a regression to get information about some market that'll give you insights that are sort of intuitive, right? Law of demand, we know the price and quantity would move in opposite directions or whatever. Sometimes you might have a situation where, you're trying to figure out, how much is the price of lottery tickets affecting, the price of oranges? Something weird. Like you want to find out some weird connection. Are they actually related? Are these variables related? Well, you would do a statistical analysis. You would regress the one you're interested as far as being dependent on the one you're interested as being independent and affecting it. And then in that case, the results would be very powerful because the T statistic would tell you, well, in reality, if you were to do this a lot, then the impact might be 0, meaning that there really is no relationship. Even though you have estimated some value, it's not what we call statistically significant. It's not actually predictive. So the T statistic will have some value in this approach in most contexts. In a demand context, if you're looking at quantity demanded as a function of price, then the T statistic is going to be large because we know that that is a valid explanatory variable of price, of quantity demanded. So this is not a surprising result here, but again, this sometimes will give us some insights that are important. So the reason for this, the fact that if the T statistic for a parameter is large in absolute value, then you can be confident that the true parameter is not 0, meaning that the parameter we've estimated is statistically significant. The reason for this is that when the absolute value of the t-statistic is large, that means the standard error has to be small, right? Because you're dividing the coefficient estimate by the standard error. So one can be more confident that given a different sample drawn from the true model, the new parameter estimate will be in the same ballpark. Regression packages also report the p-values, which are much more precise measures of statistical significance. So they're another way of sort of gauging statistical significance. In this case, for our price coefficient estimate, we know we got a p-value of 0.0012. And what that basically tells us is that there's a 12 in 10,000 chance that the true coefficient of price is actually 0. So it's the probability that what you've estimated is not valid. So obviously the probability is super low here, which makes sense because we know that that price does affect quantity. But again, that's another important value that is often looked at whenever you're sort of analyzing the legitimacy of a statistical analysis. So just understand the p-value what it is, understand the t-statistic what it is. Usually p-values of 0.05 or lower are considered low enough for a researcher to be confident that the estimated coefficient is statistically significant. If the p-value is 0.05, we say the estimated coefficient is statistically significant within the 5% level. So we see that the p-value reported for the coefficient of price implies that it's statistically significant at the 0.12% level, and therefore the estimated coefficient is highly significant. As far as t-statistics go, the rule of thumb for those, when the absolute value of the t-statistic is greater than 2, the manager can be 95% confident the true value of the underlying parameter of the regression is not 0. As long as it's 2 or above, then we know that our parameter estimates are statistically significant, just from the t-statistic. But it's important to have a lot of diagnostic statistics that are kind of supporting the statistical significance of what you've done, because again, there are ways of attacking the overall approach. And so even though you might have a clear-cut result based on what you've done, somebody can attack your approach. And therefore, if the approach itself is telling you more than one signal that what you've done is valid, then that's good ammunition to sort of back up the results that you got. All right, so there's other statistics that we're going to look at here, diagnostic statistics, that not just help us understand the statistical significance of the coefficients that we've estimated, but also the overall relationship that we've decided to use. So here I decided to just study the effect of price on quantity demanded. So the question is like, is that a good specification of that relationship? Or maybe it's a crappy one. Maybe I should have thrown more things in there. Maybe just that relationship represents a bad relationship. And so we have other statistics that tell us things about the relationship itself that we've chosen, the specification of whatever we're studying. So we have a linear specification. So we can see if that approach is valid via some of these other statistics. So in addition to evaluating the statistical significance of one or more coefficients, one can also measure the precision with which the overall regression line fits the data. Two values frequently are used to measure the overall fit of the regression line: the R-square statistic and the F statistic, which is not on here. I'll show it in a second. All right, so the R-square, also called the coefficient of determination, tells the fraction of the total variation in the dependent variable that is explained by the regression. So we have our dependent variable, it's quantity demanded. We can look at the variation of it by getting the average of them and then seeing how much all those values are varying from the average. And that tells us sort of the variation of the dependent variable. So from your data, from all those points that you have, you can get that variation. You can see what kind of variation is there in that variable in the market that we're studying. And then we compute the R-square as the ratio of the sum of squared errors from the regression to the sum of squared errors total. So essentially what those two numbers are is the explained variation by the equation that you use as a fraction of the total variation that we observed in the dependent variable. So we, again, look at how much our dependent variable is varying in the data points that we have, and then we look at how much our dependent variable that we've estimated is varying. So remember, you're going to estimate a line, and then you can plug in the prices into that line, and it'll give you a quantity demanded based on that linear relationship, which won't be exactly the quantity demanded you saw in nature, because again, like some of those points varied. So, so the estimated dependent variable values will have a variation as well, right? You can get an average of those and see how much they're varying from that average. And so that's the explained variation. And then, so R-squared tells us how much of the total variation we see in our dependent variable is explained by the model that we've estimated. So it's the sum of squared regression over the sum of squared total, which I don't expect you to know like what this stuff is, but you should kind of have a general idea of what this is. All right, so let's say the R-square is 75.75. That means that the estimated demand equation explains 75% of the total variation in TV sales across the sample of the 10 outlets that we're studying in this example. The value of the R-square ranges from 0 to 1. It's either going to be 0% or 100% of the variation being explained. The closer R-square is to 1, the better the overall fit of the estimated regression equation to the actual data. There isn't a rule of thumb, though, for that value, like what makes a good R-square versus a bad R-square. So there's no simple cutoff that can be used to determine whether an R-square is close enough to 1 to indicate a good fit. It will depend on what kind of analysis you're doing. With time series data, where you look at the value of a variable over time. So let's say you're looking at the value of output for the economy over, like 20 quarters or something. That's a time series for that variable. So when you're doing a time series analysis, R-squares are often in excess of 0.9. With cross-sectional data, where you're just looking at a moment in time and how some variables are affecting another variable in a moment, then with that type of analysis, R-squares below 0.2 are not uncommon. So it depends on what you're doing, and then you kind of have to compare it to like similar analysis that have been done and kind of say, well, in relation to these other results, my R-square was a little higher, a little lower, and therefore better, worse, whatever. It's a relative sort of insight that you gain from it rather than absolute, where it's like clear cut. And that's one of the drawbacks of the R-square. It's a subjective measure of goodness of fit. Another problem with the R-square is that it cannot decrease when additional explanatory variables are included in the regression. So you can just throw in a bunch of variables into your regression equation and explain more and more variation in the dependent variable seemingly. But part of that increased R-square is just a result of the nature of how it's calculated, which is a drawback of it. So the way it's calculated basically leads to it increasing as you just throw in more variables. So you can throw in your grandmother's age and like whatever, like weird things to affect quantity demanded of televisions, and R-square will increase. So if we include, again, income, advertising, and other explanatory variables in our regression, but held other things constant, we would surely get an increase in the R-square. Eventually, the number of estimated coefficients increases the number of observations, and therefore we would end up with an R-square of 1. Sometimes the R-square is very close to 1 merely because the number of observations is small relative to the number of estimated parameters. For this reason, many researchers use another version of the R-square called the adjusted R-square, which we put a bar over. And this is how we estimate the R-square. Don't worry, you don't need to know the equation. You just need to kind of understand that the normal R-square is imperfect because it's subjective, and also that it gets bigger as you add more variables, and that the R-square solves that problem. The adjusted R-square solves the problem. So when n is the total number of observations and k is the total number of coefficients that are being estimated, In performing a regression, the number of parameters to be estimated cannot exceed the number of observations. So that's just a general rule of thumb for regression. If you have more parameters than you have data, your results are crap. The regression has not worked. So you need more data than you have parameters. But this is our R square. The difference here, n minus k, the number of observations minus the number of parameter estimates, represents what are called the residual degrees of freedom after conducting a regression. So we can notice here that the adjusted R square penalizes a researcher for performing a regression with only a few degrees of freedom, that is, estimating numerous coefficients from relatively few observations. So instead of it just adding more sort of variation that's explained by adding more variables, this measure actually hurts, is penalized, is lowered when you increase the number of parameters that you're using to explain your dependent variable. So again, if you throw income in there, you throw price of related variables, it'll actually hurt the R square. And you can see that here, as this number gets bigger, then this number gets smaller. So a number minus a bigger number is smaller. You're multiplying a number by a smaller number. This gets bigger. So 1 minus a bigger number will get you a smaller number. So that's where the relationship justifies the intuition about the statistics. I don't need you to know this again. Just understand what the R square is versus the adjusted R square and why the adjusted R square is better. So in our example, n equals 10 and k equals 2. For these data, it winds up that the R square and the adjusted R square are pretty close. Therefore, the high R square is not the result of excessive number of estimate coefficients relative to the sample size. It actually does tell us that the equation that we estimated does a good job of explaining quantity demanded. Just including price is good enough to explain how quantity demanded changes in a market, which is why we generally do focus on that one relationship a lot in these courses, because it's a powerful one. It's very strong. And finally, the F statistic, another statistic that helps us to measure the goodness of fit of the relationship that we've specified. So an alternative measure of goodness of fit is the F statistic. And why it's good is because it provides us not just a measure, but also a diagnostic statistics for it to tell us how statistically significant the F squared is itself. So the F statistic provides a measure of the total variation explained by the regression relative to the total unexplained variation. The greater the F statistic, the better the overall fit of the regression line through the actual data. The primary advantage of the F statistic stems from the fact that its statistical properties are known versus the R square, where you don't know the statistical properties. You can't say that it's a strong predictor of how all R squares might land if you continue doing this kind of regression. But the F statistic does provide you that insight. So one can objectively determine the statistical significance of any reported F value. The low reported number in the example means that there's only a 0.12% chance that the estimated regression model fit the data purely by accident. So we know that it fit the data pretty well, and it's not an accident that that is the case. It's a valid relationship. It's a valid specification of it. And so the line that we used is pretty good. So as with p-values, the lower the significance value of the S statistic, the more confident you can be of the overall fit of the regression equation. So the lower this is, the more confident you can be that this explains a lot. Regressions that have F statistics with significance values of 5% or less are generally considered significant. All right, so that was just a very standard single regression. So you can do what's called a multiple regression, where you have various variables affecting the dependent variable, and you can also do a regression for nonlinear functions, like the log linear function that we looked at right before we started this section. So again, the techniques to estimate linear demand functions with a single explanatory variable can also be used to estimate the nonlinear demand functions. The same tools can be used to estimate demand functions in which quantity demanded depends on several explanatory variables, such as price, income, advertising, and so on. So for nonlinear functions, so here you might have a bunch of data points, and we see that the curve is a better fit for that relationship. So that's, I can't give you an example because, again, it varies based on the analysis you're doing. So it could be one thing one day, it could be something different the next day. So it just varies. But it's important to understand the approach. If your data does not look linear, it might look like this, where you have small increases in quantity demanded, and then large increases in quantity demanded, depending on what price is. So here it appears that the price and quantity are not linearly related. The demand function is a curve. The log linear demand curve that we explained earlier, that we examined earlier in this chapter, has such a shape. So the log linear specification will fit this data better. To estimate a log linear demand function, the econometrician takes the natural log of prices and quantities before executing the regression. So you've got, a column of quantity demanded data. You've got a column of price data, and then you just, use Excel functions to say, give me a new column that is the log of this column, and then give me another column that's the log of the other column. And now you've got the logs of both of them, and now you can say, regress the log of this one and the log of this one, and there you go. You get your estimates. So you can have a simple relationship where you take the log linear approach to just price, quantity as a function of price. So one can use procedures identical to those described earlier and regress the transform Q and P values to obtain parameter estimates. Recall that the resulting parameter estimate for beta subscript P here is the own price elasticity of demand. So since it's a log linear demand function. So if you just want the estimate of the elasticity, you can transform your data into log linear data and then do a regression to get your elasticity. And then the statistical diagnostics that you get can tell you if that's overall a good fit or not. But at the very least, even if it's not a good specification, you can easily get the elasticity from it. Also, if you have multiple variables in there and you have a multiple regression, then the technique is exactly the same. For the case of the linear demand relationship, one might specify the demand function as this one here that we've seen before, where again the alphas are parameters to be estimated, and again price of y, m, and h, we know what those are. Provided the number of observations is greater than the number of parameters to be estimated, one can use standard regression packages included in spreadsheet programs to find the values of the parameters that minimize the sum of squared errors of the regression. So with something like this, you're estimating 1, 2, 3, 4, 5 parameters. So you need at least 5 data points. 6 is better. And then again, the R squared, the F statistic, the T statistic, and the confidence intervals for multiple regressions have the same use and interpretation described earlier for the case of a simple regression with one explanatory variable. And just briefly, what the rest of this says is basically, econometrics is a powerful technique, but even if you take introductory courses in a bachelor's program, that's still not truly teaching you econometrics. Econometrics is its own subfield of economics, and it takes years of studies to truly master it. You have to learn what's called linear algebra. Linear algebra is a form of algebra where you are multiplying sets of data with columns and rows, right? So it's kind of like normal algebra, but it has certain rules that allow you to transform data from one form to another, and ultimately be able to multiply, divide, or whatever to get to the methods that justify why a linear regression works and why all other regression techniques work. So to truly understand it, you need to know linear algebra. And again, that is beyond the scope of this class. But it is important for you to kind of just have a basic understanding of the approach, how it works, some of the diagnostics, etc., which is what we've covered here, and that's what I would expect you to learn. But in practice, definitely, if you can, try to get the assistance of like an econometric specialist. All right, we are done with the chapter, folks. Congrats, you've survived 3 chapters so far. So again, I'm going to open up 3. I'm going to open up 4's homework as well. It's up to you. we're moving along. The exam will be here soon. So, keep that in mind. I hope everybody has a good week, and I'll see you on Tuesday.